Hello again. Okay, so now we're on to part C of this problem. If you remember, in the problem we've got some particle I've labelled A decaying into two photons back to back. We worked out that the energy of the two photons is half the rest energy of the particle decaying each, and that the momentum of the first photon is MAC upon 2, and the momentum of the second photon, because it's going the other way, is M minus MAC upon 2, with in each case the direction of the momentum being parallel to the x-axis. So they're back to back, is the x-axis. Right, so the next part of the problem, part C, asks the question, what's the energy of photon 2? Right, now for photon 2 we again write down the Lorentz transformation, so that E primed equals gamma times E minus beta PC. Now we know that beta equals 3/5, and so we can solve for E primed as long as we put in the right E and PC. Well, it turns out in this case PC equals minus E, so that in this case E primed equals gamma times E minus beta times minus E, or gamma times 1 plus beta times E. And we know that E equals MAC squared upon 2. So that, well, let's express it in terms of E, because that's what we did for the other photon. So in this case, we know that beta is 3/5. Gamma equals 1 over the square root of 1 minus beta squared, which equals 1 over the square root of 1 minus 9/25, which is 1 over the square root of 16/25, which equals 5 over 4. We shouldn't be surprised that gamma is bigger than 1, because it always is. So that means that E primed equals 5 over 4 times 1 plus beta. Now beta is 3/5, so 1 plus beta is 8 over 5. The 5's cancel, and you end up with that E primed equals 2E. So for gamma 1, E primed equals 1/2 E. Gamma 2, E primed equals 2E. And so notice that the modification in the energies are reciprocal to each other. Why is that? Well, the reason is because, again, of Doppler shift. If you imagine that you've got two photons, one going in one direction, one going in the other, with respect to a stationary particle at rest, if you move to a different velocity, then one of the photons is going to increase in energy by a factor of the square root of 1 plus beta over 1 minus beta. That's from the Doppler shift formula I taught you in year 1. The other particle's Doppler shift is going to be the same numerical factor, except there's going to be a sign change on the beta. So you get square root 1 minus beta over 1 plus beta, which is the reciprocal of the modification of the other photon. In other words, one photon gets a frequency boost of a factor of A, whatever that is, and the other photon gets a frequency boost of a factor of 1 over A. And that's the origin of the fact that the modification of the energy scales as the reciprocal in one particle as the other one. Okay? Now, last part of the question, for a general beta between 0 and 1, any beta, we're not just talking about the beta that leads to a modification of a factor of 2 in energy anymore, we're talking about any beta, so I'm going to be doing algebra again rather than arithmetic, which I prefer. I know you don't, but I do. Okay, for what value of beta, for any value of beta, find an expression for the sum of the energies of the two photons. In other words, add the energies up and express that in terms of sum or all of gamma, beta, Ma and C. Okay, so we can do that. So one of the photons has, let's do gamma 1, E primed equals gamma 1 minus beta times E. And for gamma 2, E primed equals gamma 1 plus beta times E. Right? So sum of E prime 1 and E prime 2, that's going to be equal to gamma E times 1 minus beta plus 1 plus beta, and we end up with the betas cancelling, and you get 2 gamma E. But E equals mac squared upon 2. So 2E equals mac squared. So that E1 prime plus E2 prime, the sum of the energies of the two photons in the moving frame, equals gamma times mac squared. Now this brings up an interesting point. All right? The interesting point is that you could have actually come to that result a completely different way. You know that energy is conserved as long as you stay in one frame before and after the decay. Right? Now let's stay in the moving frame. Right? If in the moving frame the total energy of the decaying particle is gamma times its rest energy, so gamma times mac squared. Now after the decay all you've got is these two photons. I don't have any, so that the sum of the energies of those two photons is in fact the total energy of the original particle before it decayed, gamma times mac squared. So the answer is that E gamma 1 primed plus E gamma 2 primed has to equal gamma times mac squared. So you could have just written down this result instead of calculating it out like I just did. Now if you'd have done that and you were a reasonably ordinary undergraduate, one who might have some of the attitudes that I know people do have, you might take a look at the exam question and go, I can't believe that just that little piece of reasoning is worth 4 points. All I did was say, well, the energies of the photons have to add up to the energy of the original particle, which is gamma mac squared. How is that worth 4 points? Well, the answer is that that requires some thought and some physical insight and an awareness of the conservation laws that apply. And I'm perfectly happy to give lots of marks to students who've developed that awareness. I don't care that they don't have to write down a whole lot of algebra to get there. It takes courage to make a simple statement which is correct, rather than writing a page of algebra. And so I do encourage you not to necessarily read too much into the number of marks allocated per part of the exam question. Marks are just not just for algebra, they're also for thought. And thought is often harder than algebra. So don't be intimidated by something that appears to be too easy for the number of marks it deserves. Things aren't always that simple. Okay, so last thing in this revision lecture is to remind you of some very simple truths. You will do a lot better on exams if you read all the questions before you start and strategize. Do the questions which you are going to find easiest first. It is every year apparent to me that the students who go through the questions in number order 1, 2, 3, 4, 5 quite often miss huge numbers of easy marks. This question is last on the paper. That does not mean it should be the last one you do. If you've enjoyed the course, if you think you understand relativity, if you've prepared well for the exam, do at least consider doing this question sometime other than in the last 2 minutes. Of course, I'm letting myself into some more marking by saying that, but I don't care. I want people to try this question if they feel able to. And the second piece of advice is much more normal and common sense. Make sure you know how to get to the exam hall. Make sure you get there in plenty of time. Make sure you have slept well. Keep to your normal routine as much as you can before the exam so your body's in its normal metabolic state and so that your mind is as clear as it can be. And the very best of luck. Okay, bye.